It's really my honor to be here to give you a little bit of a brief review of what we are doing at Duke. And so today I'm going to focus on exploring candidates that could host Dirac quantum spin liquid states in them and what we have done in that regards. So first I would like to make the acknowledgements. So all the work that I'm going to show you, the neutron scattering work, were collected at NEAS Center for Neutron Research, Oak Ridge National Laboratory, both SNS and HIFER, the ICES Neutron Muon Facility. And I will also show you some high magnetic field data, which was collected at MagLab. I have been really privileged, and I have to say that because it's very important for experimentalists to have connections and to have the insight from the theory side. So we have been very privileged working with great theoretical researchers. So some of the work was done, the older work that I'm going to show you, it was done by Sasha Chernyshev's group, and some of them also by Christian Batista's, but the more recent work that I'm going to show you was in collaboration with Joel Moore's group at Berkeley. And also I would like to mention that Patrick Lee has been really helpful for both Joel and myself and giving us some insight into how to interpret our data. And the work has been funded by NSF and DOE. But of course, I would like to also acknowledge my team back at Duke. So the work that I'm going to show you, the older work, was done by William Steinhardt, and who since graduated. And some of the work that I'm going to show you was done, the recent work by Rabin Bag and Lalit Yadav, as well as Matthew Innes. Okay, so I'm pretty sure that you all know about this, but just as an introduction into the talk. So what I'm really interested in are frustrated quantum materials, and there are different ways that you can have a system frustrated. If you focus on the 2D systems, of course, if you can a geometry that would give frustration, that would be one way to look at it. So for example, if you have a triangular lattice antiferromagnet with the Ising spins and antiferromagnetic interactions between them, so the spin will be up, this would be down, and this side would be frustrated. But also, and so this is basically the triangular lattice is what I'm going to focus on, and this resonancing valence bond by Anderson was proposed for a triangular lattice. Now, you can also have different types of frustration. For example, you can have a competition between exchange interactions. So if you have a square lattice antiferromagnet, for example, the nearest neighbor and next nearest neighbor interactions can give us frustration, which one of the very well-known examples of it is the chassis or Relan systems and models, which I have also been working on this, but the focus today is going to be on triangular lattices. Of course, in 3D, we can also have frustration. For example, the pyroco systems, which have the corner sharing tetrahedra. So that can also be a way that we can create frustration. So actually, we work on all of these different systems. And today, I'm going to give you introductions onto what we have been able to achieve with the triangular lattice. Okay, so today, I'm going to focus on two different compounds, which are from the same family, and but they have different physical properties. So the first one is ytterbium-based triangular lattice system. So a while ago, I believe in 2015, this compound, ytterbium, magnesium, or zinc, gallium, oxygen 4, has emerged as a candidate for quantum spin liquid state. At that time, actually, the discussion was that this system has a spin on Fermi surface. So that would be the way that you can think about the QSL state for it. So there have been a lot of work that was done on it, for example, in elastic neutron scattering, MUSR, heat capacity, other experiments, that they all revealed that there is a spin liquid-like behavior in this compound. So here you're looking at the crystal structure of this particular compound, which I'm going to call it 1114. So the one would be the indices for each element. So if you think about this, so the ytterbium 3+ has an effective spin 1/2, and it is forming this triangle. So here you're looking at the AB plane. So these triangles in blue are forming by the ytterbium 3+. And then, so they're basically quasi two-dimensional. You have the insulating layers in between them. So for example, you can think about the gallium with zinc or magnesium. The challenge that this compound had actually showed us, as specifically somebody who also synthesized materials, is that you can see that there's a 50% chemical site mixing between gallium and zinc or gallium and magnesium, which has actually made the interpretation of the data very complicated. So at the same time, there have been some pressing questions that are talking about the fact that what would be the effect of this chemical disorder? And it is very significant, 50%, 50%. And so they talked about various theoretical models that would say that this compound, if did not have the chemical disorder, would order, and it would just form some sort of a stripe ordering. However, because of this chemical disorder, it's just mimicking what the quantum spin liquid state would do.
Are these insulators?
They are insulators.
So every time you say order or anything, there's
magnetic
spins.
ordering,
Right.
spins ordering. That's right. Yes. Okay. So so there have been a lot of debate actually regarding this compound and what exactly is happening in it. So by the time that I started to pay attention to this system, most of the ambient condition measurements were done. So we were able to synthesize the material. We also observed that there's chemical disorder. However, what was lacking was that a field dependence, or using a magnetic field as a tool to understand the physical phenomena a little bit better. So here what I'm showing you is basically neutron scattering data integrated over energy, and you're looking at the Q space. So this at the zero fields, and these are all done in millikelvin temperature. So we are in the quantum mechanic regime, and you don't have a lot of thermal fluctuations. So you can see that this is the basically zone boundaries, and you can see that at high symmetry M points, so here I'm showing you the M points and the K points at the corners, you're getting more excitations, and then you can also track the zone boundaries very well with additional excitations at zero field. This is actually in agreement with what was proposed as a quantum spin liquid candidate, as well as maybe it is ordered and just mimicking that. And the reason for the in effect that it could be really ordered, but it's forming some sort of a diffuse scattering, was the chemical disorder. What we did was actually we went.
I'm sorry, may I ask a question about that? Right. So, if it were, the point is that if it were really ordered, yes, or then you would expect to see Bragg peaks at the M point?
Yes.
Is that the point?
Yes.
And so what's observed here is an enhanced intensity, but not a Bragg peak.
But not a Bragg peak. Okay. Very diffuse. Yes, that's right. Which from different models, so somebody would say that you see this diffuse scattering, but it is practically coming from the spin on Fermi surface. Okay. So what we did was that we went up in the field. So we were very patient actually. We started to go up in increments of 1 Tesla. And so at 1 Tesla, we actually start to see that you see that the intensities at M point are now more homogeneous. But look what happens at 2 Tesla. At 2 Tesla, the intensity which was at M point is now shifting to the K points. And when we started to go even higher in field by above 5 Tesla, it starts to go away. You lose all the excitations and the intensities. So when we collected this data, we got in touch with Christian Battista's group, which they were working on triangular lattices. And then we mentioned that this is what we are seeing, and this has not been seen before. So whatever the model we predict for the zero field, it needs to also follow this rule that when you start to apply the field, it needs to have this phase crossover between the M point and the K point. So this is what they have actually done through iterations and classical quantum, classical Monte Carlo simulations. And what they did was that basically they used the model that was already predicted for this compound, which is an XXZ model. And then they said, okay, so when you have this XXZ model, let's start to look at it in 2 ways, quantum fluctuations or site disorder. And then through both of them, actually, we were able to replicate the zero field data. However, as I mentioned, when you have the chemical disorder and everything is very diffuse, then it is going to be very difficult to look at the order parameter space. And in order to figure out what is the order parameters, what is the value for the exchange parameters. But what we had is a tuning parameter saying that whatever we come up with needs to follow this trend. So they were able to find a set of parameters that would actually basically comply with our experimental data. Here I'm showing you the line cuts across the zone boundary, for example, in here at different fields. And you can see that the endpoint is being picked up at 0, and then it starts to go to the K points. And this is the simulation that they were able to get from these order parameter values. The whole point of this work was to say that even if you have site mixing in a compound, it's not a death sentence. And there may be some tuning parameters like the magnetic field or the pressure that would give us some other additional information that we would be able to extract the order parameters a little bit better. So here is basically it's a summary of what we have done. So there have been some single Magnum dispersion at about 7.8 Tesla, which actually we looked at the cost function comparison to the experiment for this. But as I said, this was very diffuse. And then we looked at this crossover as well. So here, basically, we are showing you what were the proposed values for the different exchange parameters initially, and then these are how we were able to constrain the order parameter space based on the transitions that we saw as a function of magnetic field. So I'm not going to get into too much details about this. If you're interested, this was published a while ago. Please have a look at this or talk to me later on.
But again, I'm sorry, may I ask this? Are you willing to say at this point, well, what's the bottom line? Is this shift of K points and so on compatible with a conventional ordered state plus some site disorder, or is it incompatible?
It's compatible with both of them,
okay,
actually.
So it's compatible with
it's
both
compatible, however, we were able to constrain these values, right? And actually, so here, this is a nice comparison. So here, basically, this is our parameters that you can see that at different fields is showing that how it's going from the M points to the K points, for example. These are the parameters that were basically allowed by different models. So these different models, so for example, they have values that correspond to the ordered state, or they have values that are corresponding to the quantum spin liquid state. But actually, none of them were able to replicate what we have seen. So we were able to contribute to this by basically looking at the different fields. What we also have done with regard to this 1114 compound was basically we made the compound, so this previous one was with magnesium, then we made it with zinc. The reason that we've decided to look at zinc is that if you think about the zinc 2+ and gallium 3+, they have the same electrical composition. So if there is, well, not if, we know that there is a site mixing. So what happens if you try to basically suppress the electrical fluctuations by picking the two compounds that are closely related to each other? So that is what we have done. And by doing that, we were able to look at the inelastic neutron scattering. So here you're looking at the energy versus Q. And again, we started to look at different fields, 0, 1, 2, 3, and 4. And also we went up to 8 Tesla. And we were able to see what is basically looks like a continuum of excitations. So this, you can see that it's very diffuse. And even in this case of the 8 Tesla, you can see that it is rather diffuse. So the fitting of the spin wave spectrum is going to be challenging. But again, what we did in this case, we were able to use the linear spin wave theory. And we said, okay, in this case, let's just focus that if it was ordered and you had the site mixing, how it would be able to replicate the data. And we were able to come up with the set of parameters. So again, here, if you're interested, this was published also a while ago. Let's just have a look at that or discuss with me later. Yes.
Sorry, just want to have a basic cartoon. So you have a terbium, you have magnesium or zinc, and something else. So the magnetic ions are
not site disorder, they're fine.
I see. So
the
disorder is only in the pattern of interactions.
Yes, yes.
And you started by talking about frustration. Was there frustration in the putative clean? limit, or are you relieving frustration or inducing frustration? I guess I'm
So
not
we
sure.
think, so that is the question. We really don't know, because if when you have the site mixing, it's gonna change the order parameters, right? So we don't know if not ordering is a result of having a triangular lattice with a set of interactions, or it's because of the chemical disorder.
Okay, but in the attempt to match this with a theory,
yes,
the output of that theory is some sense of how strong variations of J
yes,
are
yes.
induced. And so just for us to remember, is it like 50% variation, or is it
For the J?
Yeah.
It's actually, it's I would say it's more than 10%. Yeah, so that it would actually vary it quite a lot. I will show you with so it will become a little bit more clear as we move on. So, but if you're interested in this work, which we assume that it is ordered, you can have a look at this, which the data, again, you can see that they are in a good agreement, but not perfect. Now, what are the takeaways? So as somebody who synthesized materials as well, all of this work actually gave me two lessons. The first one is that the rare earth quantum spin liquid candidates are emerging that show these sort of field-induced transitions. And so I call the terbium the new copper for us, because it is actually giving us a lot of information. There are different candidates out there, and it's not very difficult to make. So the other point is that, so the chemical disorder is complicating everything. So what if we try to limit the chemical disorder, or at least minimize it as much as possible? That's one way to think about it. Or if we want to study there are some theories out there that the chemical disorder can induce, for example, quantum spin liquid candidacy. In that case, in a controlled manner, add chemical disorder. So today I'm going to talk about our efforts in trying to minimize chemical disorder in these compounds, and then we would have a more clear picture of what is exactly happening in them. So this is the 1114 compound which we've just discussed that has the chemical disorder between gallium and zinc. So here you have the triangles. With ytterbium 3+, this is the chemical disorder between gallium and zinc. And you can see that it's having a space group R-3m. So this is the distance between the two magnetic layers. And also you can see that the A, B, and C are the lattice parameters for it. What we have done is basically we deliberately tried to put a zinc oxygen layer in between these two layers. So by doing that, what we have done is that we gave each element of the gallium or zinc its unique Wyckoff position. And we changed the space group as well. So by doing that, we were able to eliminate this 50% site mixing, so that we would have a clean compound that we would be able to study and then extract the physics out of it. So I'm going to call this ytterbium zinc 2 gallium oxygen 5, which has an additional zinc oxygen layer compared to this compound, a 1215 compound. So we have a 1114 with chemical disorder, and we have a 1215 compound without chemical disorder. So we attempted for this, but of course we need to make sure that it really doesn't have chemical disorder, right? So here I'm showing you the single crystal compound that we were able to grow back at Duke. And you can see that it's very transparent, so it has very high quality. This is a Laue pattern for it, which you can see again, it's showing that it's a high quality single crystal. And then we did the powder XRD and actually on a crushed single crystal compound. And we were able to look at the pattern, and we were able to fit this with a structure, with a new structure and no chemical disorder. So the fitting actually worked really well. And then we intentionally started to add chemical disorder to see if the fit improves or what will happen to it. What if there's a chemical disorder and we don't detect it? And actually, when we did that, the fit value, the goodness of the fit went down. So it actually shows that the chemical disorder is not favorable in this particular case. However, when you think about it, the zinc 2+ and gallium 3+, they have the same electronic configuration. So in the eye of X-ray, they are practically kind of the same because the X-ray look at the electrons, right? So in that case, one would say that the cross sections for the gallium and the zinc, they are the same. So maybe you're just blind to the chemical disorder when you look at it with X-rays. That is when we actually started to look at it with neutrons as well. Because for neutron scattering, the cross-section is completely different for the two, right? So by doing that, we were able, again, to fit the data. And by fitting the data with no chemical disorder, we were able to get the best results. So these data sets are showing that at least within the resolution of our experimental techniques, we cannot see any chemical disorder. So that's a very good news. Okay, so the next step is that if it is truly now this new compound, if it's truly quantum spin liquid candidate, one of the signatures of it is that when you cool it down to very low temperatures, it should not order, right? At least in the case of the triangular lattices, I have to open a bracket here for Kitaev quantum spin liquid candidates out there. Some of them order a zero field, and then they start to give quantum spin liquid features when you apply field. But we are not talking about that. In a triangular lattice, then the one way is to look at it at very low temperatures. So you're looking at the DC susceptibility as a function of temperature. And basically, this was done down to 300 millikelvin at Duke. And we were able to look at the two different orientations for the field, and none of them are showing any features that would be indicating of the ordering down to 300 millikelvin. And we also did the zero field cooling and field cooling. By doing that, you would be able to figure out if there is a spin freezing, because if it starts to show a hysteresis, it means that you have a spin freezing. And we were not able to see that down to 300 millikelvin. And then, so here you're looking at the Curie-Weiss fitting at the low temperature range. At the higher temperature, you have this crystal electric field effect that will come in. So we did it at low temperatures. And you can see that the exchange parameters getting off of this Curie-Weiss fitting is basically incomparable with what we see for a little bit better than 1114 compound. But of course, you can also see that there is an anisotropy associated with this when you start to look at the different fields. Okay, so to better understand the anisotropy, we also did the magnetization measurements. So here you're looking at M versus H and up to 14 Tesla. So this was collected at 2.5 Kelvin. And it was basically for us to see when you will have strong enough magnetic field to start to polarize all the spins, right? And also to look at the anisotropy as well. So you can see that for the two different orientations of the field, there's a clear anisotropy. And I would say at around 10 Tesla, you can say that both directions are starting to have the spins polarized as a function of field. Okay. Now, if we have a state that does not order, doesn't necessarily mean we have a quantum spin liquid. It could also have the spin glassy nature of it, right? So another way to look at that is basically to look at AC susceptibility measurements. So this data was basically collected, part of it was collected at MagLab, and part of it we were able to collect it at Duke. So what we have done, basically, you have looked at the AC. So this is the real part of the AC susceptibility as a function of temperature. And you can see that basically the data can extend down to 20 millikelvin, so even further down in temperature. And you can see that there is a peak that appearing. And at very low frequencies, here you're looking at the different frequencies, and this is temperature. There's a little bit of a shift, but then it starts to come back. And so if you look at the highest frequency and the lowest frequency, they're practically at the same, the peak is at the same temperature. So this is an indication that there is something going on, which we need to understand because it's giving us a peak, but that peak doesn't show a clear frequency dependence that would say that you have a spin freezing of the state. We anticipate that this is coming from an orphan spins, because when you have even if when you try to have the perfect crystal in experiments, there may be some defects, and we think that they may be coming from those defects. However, the good news is that when you look at the lowest basically frequency, and then you try to do a linear extrapolation of that, you can see that it crosses very close to zero. So that's a good indication that at least it doesn't get to a finite value that would be a glassy nature or something that makes things complicated. Okay, but we didn't stop there.
But excuse me, may I ask a question about that? So if this is orphan spins, then presumably its magnitude should be small.
Yes.
Now I see you have written AU there.
Right.
But do you have a sense of how many spins, I mean, even roughly how many spins are participating in this behavior?
We think it is less than 2%.
How do you know that?
We did the same measurement with our PPM. So this was done at MATLAB, and then we did, so at MATLAB, it's not calibrated, or coil or not. And then we did it with the PPMS and we matched it together. Okay, thank you. Okay, so there is another way to look at the dynamics of the spin at very low temperatures, right? And that's by looking at the Kolkol plot. So in a Kolkol plot, you're looking at the real and imaginary part of the AC susceptibility. And basically, there is going to be this parameter alpha. And this parameter alpha, which you can see, so this is a Kolkol equation, and this is the parameter alpha that kicks in here. So this is basically talking about the distribution of the relaxation times, okay? So if you start to have alpha close to zero, you will have a single relaxation time, and it shows that the spins are dynamic. If you have a value of alpha that gets close to 1, so for 0, it would be a semicircle, and for getting to 1, it would be very flat. So it means that you have a multiple relaxation times, which would be an indication of the spin freezing or a glassy nature of the spins. So we have done this, and we have done it at down to 20 millikelvin, and you're looking at the different values for different temperatures. So here, when we feed our data to the Kolkol equation and extract the alpha parameter, you can see that for the different temperatures, all the values that we are getting is very close to 0. And in fact, for 20 millikelvin, this is the lowest value that we get. This is an indication that the spins, at least down to 20 millikelvin, are still very dynamic. So we are more or less thinking that most likely there is no freezing that is causing the spins not to order, but it is the dynamics of them, and that could be good news for the quantum spin liquid candidacy. Okay, so the next thing that we checked is basically to look at the heat capacity. And this actually turned out to be quite important. And the reason for that is that, so the first thing to check is, okay, down to 50 millikelvin, is there going to be any ordering that we would be able to see at in a specific heat? And of course, we didn't see anything. You're looking at the total specific heat as a function of temperature at 0 field in here. And you're looking at that there is a Schottky type of a peak that is popping up. And then, so this is for the ytterbium compound. And also we made the lutetium compound, which is isostructural of ytterbium, but it's non-magnetic, so that we would be able to subtract the phononic contributions, and we would be able then to look at the magnetic entropy. So the magnetic entropy goes to R log 2, which is indicating again to what we have seen before, which is you're dealing with a ytterbium 3+ effective spin 1/2. Okay, now let's look at very low temperatures. So if we start to look at very low temperatures, this is the total basically a specific heat. And you can see that there is an upturn. Now, when we are dealing with rare earth elements, specifically ytterbium that has a lot of isotopes, you will expect to have some sort of a hyperfine interactions due to the nuclear contributions. So this is basically what we are showing, that it's a contribution from the nuclear hyperfine. And we subtracted this off, as well as the phononic term, which is very negligible in this case. And this is what we've extracted. So this is specifically specific heat as a function of T², and there's a reason for that. So if you look that the fit that goes for the linear, and that would be the power law fit that would give us a linear behavior, doesn't fit really well. And what if you think about it, here in the T², it actually shows a very nice fit down to the low temperatures at about like 120 millikelvin. So this is actually an important outcome of this analysis. And I would like to draw your attention to this paper. So this paper in 2007, which Patrick Lee and colleagues have actually published, it's a theoretical, basically, interpretation of a Dirac quantum spin liquid candidate for Kagome materials. But actually what we did is basically we started to look at this, and this formula says that when you're at zero magnetic field, you can see that the C over T squared is basically going to be linear. So indicating that the specific heat at low temperatures, and this is for very low temperatures, at low temperatures, it needs to be T squared, the behavior of it, which is what we are seeing in the zero field as well. So that was an indication that most likely we are dealing with a Dirac quantum spin liquid rather than a spin on Fermi surface. Okay.
So, sorry, just to clarify. So I guess the confusing thing to those of us innocent theorists is how well established is the C nuclear line?
Right. So actually, when we did
exactly,
So when we fitted this, we actually checked against other compounds that they have ytterbium 3+ in them, and the value is in very good agreement with that. Yeah. So other compounds that people have seen the nuclear contributions for it, for ytterbium, they completely agree with what the values that we get for A. This is the first term for the nuclear.
Can I just clarify that a bit more? So in order to be able to subtract that divergent concentration, it's a 1 over T.
T squared.
T squared, yeah. Mm-hmm. You need a concentration of isotopes and you need G factors. Is that right?
That's right.
And those can be can those be? Maybe it's a question. Can those be measured independently? So like it's not a fit; it's just a fit-free subtraction, or do you actually fit it?
No, we actually fit it and subtracted it. Yeah, yeah. But the value for A is in agreement with the values that other people have done on different ytterbium compounds. So that's our indication that most likely it is going to be in agreement, right? And then I will show you more of this analysis with the field dependence as well. Okay, so before I move on to more low temperature stuff, so this is basically the inelastic neutron experiment that we did on a powder compound, just to look at the crystal electric field excitations. And here at 40 MeV, there's the first excitation, and then you have at around 60 and around 90. There are these excitations, and ytterbium is a Kramer's ion with J 7/2, and so we expect 3 excited bands for it, and we observed all 3 of them. Now, given the fact the first excited state is gapped from the ground state by 40 MeV, it's an indication that we are having this pseudo, basically effective spin a half for the ground state of ytterbium, if you look at it from single ion physics. Okay, so this is our attempt to fit. So we did fit this with single ion physics. So we got the X, Z parameters, and these are basically the parameters that we were able to get. So it's all good, and it's all in agreement with our previous measurements. Now, let's move on to the single crystal neutron diffraction measurements. So here, again, you're looking at the Q space, and this is basically energy versus Q. So here we saw that there is a continuum of excitations, similar to the 1114 compound. However, it has a little bit of a difference, which I will bring it out in the next slides. So here you're looking at the cuts that we have made into this energy. So cut 1 is the low energy. So here you're looking that, again, it's picking up at endpoints, but it's not as significant as in a 1114 compound. And then when we go up in energy, it becomes more diffuse. And then by the cut 4, it's basically very diffuse. So 2 lessons. One is that, okay, it's at zero, at lowest energy and 0 field. So this is all done at 0 field and at very low temperatures. It's peaking again at endpoints. However, it's a little bit more diffuse, so it could be an indication of more quantum fluctuations if you're lucky. And then also the next lesson that we learned from this is that when you start to go really high up in energy, so it starts to become diffuse, and it shows some sort of a continuum of excitations. Okay, so when we were working on this material, actually Jules was visiting Duke. And when we showed this data to him, he got really interested, and he said, well, we are having this paper coming out at the time, it was on arXiv, that we actually looked at the J1, J2 Heisenberg model on a triangular lattice, and we would be, it would be nice to collaborate on this and to start to think about this new compound as well. So here what I'm showing you is the intensity as a function of Q for the neutron scattering data. The reason that I made this cut, so it's practically making a cut across here, okay? So it's picking up at endpoint. The reason that we did this cut and to start to analyzing it was that Jules' model was for isotropic systems. We already know that our system is anisotropic. So when you have an anisotropy, we started to think of how we can implement the anisotropy parameter, which would be delta, into the model. By doing this, if you have an isotropic system, basically you would have all of these peaks at the same intensity. However, when you start to have anisotropy, we thought that this effect is coming due to the anisotropy. We looked at the intensity at M point and a K point, and we got that it's about 1.38. So they also ran the model based on different delta values, and they figured out that the delta value of 1.35 is going to give us the same intensity ratio between the M point and the K point, and then started to implement this delta value into their model for the J1, J2 model, okay? So here is the energy as a function of Q for the experimental data. So you're looking at these excitations. There is basically a gap that starts to opening as we get close to gamma point, which is also important. And here I'm just basically showing you the path that we collected the data. And here's a cut at low energies. It's not basically very low energy. It's integrated all the things from 0.5 down, 0.5 MeV down. And here is the theoretical model based on this delta value that was done for the same compound. So you're looking at basically the excitations for the calculation that is sort of in agreement with what we are seeing. There are two things that they need to be addressed. The first thing is that basically we see an upturn in here, but we don't see in our experimental data for two reasons. One of them is that we have a blind spot in here. So it's very difficult to see the excitations that up here because you're getting very close to the detectors. But the other thing is that this downside that you're seeing, but there's still a gap in here. And we think that this gap corresponds also to the gap that have been seen. So the upturn goes from the K point. So this is a K point, which is in agreement with here. And then there's a gap that is opening at the gamma point. So here you're looking at, again, the simulations versus the experiment. The reason that you see them in blobs is that, so this was done by DMRG. And so there's a finite size effect that's basically making it, the resolution is not perfect, okay? So that's a good indication that so far there's sort of an agreement between the two, but of course there's still more needs to be done to definitely pinpoint that is it truly the Dirac quantum spin liquid. So to do that, we actually started to look at the data as a function of magnetic field. So here you're looking at the magnetic specific heat versus temperature. So we didn't see anything that would be very surprising that give us an indication, at least within this temperature range. So you can see that the Schottky term starts to move up in temperature as a function of field. Again, it saturates at R log 2. So it's all very good. Let me bring you back to Patrick's paper. So Patrick's paper said that when you have basically because of these Dirac nodes, when you're at low temperature and you are at zero field, you have the T squared law, okay, for the specific heat. They also looked at it as a function of magnetic field. So again, at the range of very low temperatures and very low, actually, to be honest, this turns out to be very low as well. At the low temperatures and low magnetic fields, because this is going to be a limit that the Dirac physics is going to be valid. In this case, what they said is that the C over T is going to be looking something like this, which is going to be linear with B, meaning that if you start to plot C over T at a different B values or different magnetic fields, it starts to go up as a function of that. That is what we did. So we actually looked at the data down to 50 millikelvin. And here you're looking at the data at zero field. This is basically 0.01 Tesla, and you're 250 Oersted, and then 500. So the reason that for this is that because we need to still be in this range. We need to be in this range, which itself needs to be within this range. So at very low temperatures, that would be comparable to that. But what we saw is that definitely when we start to go up in the field, the data starts to go up as well. And specifically when you start to extrapolate that to the low temperature, which is what would be the perfect scenario, it clearly shows that there is an upturn as a function of field. So that was actually very good news for us, that we were able to, at least in the second scenario, we were able to look at the different fields, and they also show what was predicted by the mean field theory from Patrick's paper. And here we actually started to go even higher in different fields. And here you're looking at the extrapolations at 0, this is 0.1, 0.15, and then so on. And you can see that when it gets to 0.5 Tesla, it starts to basically deviate from the physics of the Dirac quantum spin liquid.
Excuse me? Mm-hmm. So if you go look at those plots, mm-hmm. Those little wiggly tails, right, the lower temperatures, is this because of the subtraction scheme?
This is because of the subtractions, yes, yeah, exactly. Okay, so let me bring you back again in here. And the reason for that is that not only you would be able to look at the behavior of the specific heat at two different ranges, zero field and finite field, but also if you take the ratio of these two, right? If I take a ratio of these two, it actually gives us the actual value that you would expect to see for different fields, right? So we did that. We actually started to look at the different values for gamma and B. So the gamma would be the linear T coefficient, and B would be the quadratic coefficient. And we started to look at this data, and you can see that it starts to deviate at basically above 0.3 Tesla. And this is the crossover between them. However, what we did was basically we calculated this ratio as well, and we compared it to the theoretical value that Patrick's paper actually predicted. And here is what you're seeing. So this is our experimental data, which within the low field region follows the actual values that you would expect to see for the theoretical values. And when we start to go off, it starts to basically, a higher field, it starts to go off. So that was an indication that, okay, so this field also agrees with what we are seeing in here as well. And then so the values are in good agreement. What we also did, which I don't have it in here, was we looked at the Fermi velocity for the spin-ons. And indeed, actually, what we get is 75 meters per second, but that is much lower than, not much lower, but significantly at a lower value that you would expect for a very dynamic ground state. And that could be the reason that in this plot, okay, in here, there's the lower velocity of the spin-ons could be an indication that we also are missing this value that is shooting up. But that's a hypothesis.
So may I ask for a little more clarification in your comparison of zero field and non-zero field?
Yes.
there was an effective Bohr magneton floating around that you need to make the field into
Yes.
an energy. Did you just take that from your previous determination, or was
Yes.
that a fit parameter?
No, it was not a fit parameter. We took it from the previous determination.
And is that known to be right? I mean, the spin liquid is some kind of exotic emergent
Right,
phase, but
right.
so does its particles carry the same Bohr magneton? Is that known? All right. Well,
I haven't, I haven't, I'm not quite sure actually. So it's, all the analysis that I have done is basically, they don't fit that.
Mhm.
So
Yeah.
they just use
Okay.
it, yeah.
But then my other question is, why did you do it in this way? If I go back to your formula and your basic data, it seems to me that if the main content of this formula is that if I believe in the slope at zero field, that is equation 4.
Yes, yes.
And I know what the Bohr magneton is,
Right.
then I just know quantitatively what the zero temperature intercept of C over T is as a
Right.
function of B. Right?
Right, right.
So why isn't there just a plot of intercept versus B?
Intercept versus B.
Yeah, the C over T at that thing versus B. Just using in real numbers, using the A and A over VF squared and so on, obtained from equation 4.
I think it is because we are not quite sure about this, right?
Well, that's what I can.
That's so So the reason that we did this, to be honest with you, is that we were going to do this, and actually I did that. And then Patrick saw this, we had a discussion, and he said that the safest way is to take this ratio so that you would be able to look at the actual values for it that would not have this dependency of the different parameters. Yeah, that could be the reason mainly, yeah. Okay. So far so good, and then so for this range in the field and temperature, we think that we do have the Dirac quantum spin liquid candidate. However, something also more interesting happened when we went to very high fields. So when we went to high fields, here you're looking at the H perpendicular to C and H parallel to C, and this is the raw data. So you're looking at the 0, and then you can see that up to 4. Up to 3 Tesla, actually they are going up, and then they start to change the behavior when we pass the 4 Tesla. For the H perpendicular to C, what you can see is that when we start to go up to about like 6, they are still going up, and then when we pass that, they start to change their behavior. So we looked very carefully at our magnetization as a function of field. And you're looking at the 2 different orientations. So this was done down to 300 millikelvin. And I'm here showing you the dm dh versus h. And basically you're looking at the 2 different, so there's a little bit of a line change line shape change in here. And you're looking at, there are 2 sort of plateaus or features that they start to form in. So there's one which is at around 2 Tesla, the onset of it. And if you look at the other one, it's at around 3.7, but they start to go up to 7 Tesla, and this one goes close to 4 Tesla. They do agree with what we are seeing in here. So the change of the behavior for the 2 different orientations as a function of field agrees with what we are seeing in our dm over dh, or basically at very low temperatures. So we were not able to go to the lower temperatures, but I'm guessing that if we would go to even lower temperatures, we would be able to see this a little bit better. But with what we basically have so far, and this is just the temperature dependence of it so that you can see it a little bit better. One key point is that when you have a triangular lattice and you see a plateau or a change in the line shape, somebody can say that it's most likely it's going to be the 1/3, right, for the triangular lattices. In this case, we are seeing it actually happening at a half of the saturations, which is again another indication that there is more that still needs to be understood in this particular case. To be able to do this in a higher resolution, we actually went back to MATLAB and we did this measurement. So this is called a tunnel diode oscillator technique. The way that it works is that you have a coil, the sample sits in the coil, it's connected to an LC circuit, And then we are looking at the resonance frequency of the coil. It's a very high resolution, so it's even higher resolution than SQUID. And through that, you would be able to basically start to look at the change of the magnetization, because change of the magnetization changes L, and when L changes, the resonance frequency of this coil will start to change. So by looking at the change of the frequency, you're basically indirectly plotting what would be the dm over dh. So here I'm showing you the data. So that's the frequency and this is the field. And you're looking at it. So when we are at the zero, at H parallel to A or perpendicular to C, you see that there is this nice plateau that shows up. And when we start to go away from it to H perpendicular parallel to C, it starts to actually diminish and move down in the field. This is in agreement with what we saw in our SQUID measurements as well. So we are not quite still sure what is exactly happening in here, but we looked at the inelastic neutron experiments. Here you're looking at the energy as a function of momentum at the different fields. And you can see that there is a continuum of excitations in here, but also if you look at the 4 Tesla, you can see that it starts to show 2 different bands. So there are excitations that are appearing at K points at the lower energy, and then they start to have this band up here. Here you're looking again at these 2 different bands, and this is at 8 Tesla. That shows a very nicer dispersion compared to 1114 compound. So what we did also, we went back and we looked at the parameters that we basically proposed for the 1114, and we tried to fit this over our data. And one thing that I would like to mention is that at 8 Tesla, so this is 8 Tesla data, it's still not completely polarized. But you can see that the data that was, these dots are showing basically the simulation based on the parameters, and you can see that they don't fit very well. So we have this sort of a curvature to this higher field data set that they don't agree very well. So this is an ongoing process, but I'm going to show you the very preliminary data, which was done by Joel's group. So they started to look at the J1, J2 for the Dirac quantum spin liquid as a function of different fields for the different basically anisotropy parameter, and they're able to actually get this plateau-like features at the same, almost the same field. And when they go to an intermediate field, they also see that there is going to be excitations at the lower energies compared to this. But this is an ongoing, it's very preliminary, and we still need to work more on this to be able to understand it better. And with that, I would like to conclude that we were able to successfully synthesize new compound that we think that within our resolution of the instruments, it doesn't have intrinsic chemical disorder. We looked at the AC susceptibility measurements that shows it's dynamic. We did specific heat measurements that are showing a quadratic term. And then we looked at the inelastic neutron experiment. One other thing that I would like to mention about the inelastic neutron experiment is that the previous 1114 compound, when it was proposed as a spin-on Fermi surface, they had excitations all across the beryllium zone. And in our case, when we looked at the data, you can see that there's clearly picking up at the K point, and there's a gap opening at the gamma point. So that would be more indication that you have the Dirac cones and not a spin-on Fermi surface. And then we have identified this as a U1 Dirac quantum spin liquid candidate. I would like to draw your attention to this paper as well. So this is done by Sabir's group. And so they talk about the correlation between the Dirac quantum spin liquid spectrum and superconducting in cuprate pseudogaps. So that's, I found that this is an interesting one. And so I would like to be an advocate for further exploration using diverse range of experiments and theoretical techniques in order to understand this very interesting physics better. And I would like to thank you again. Thank you very much.
All right, so we had a lot of questions, especially from the front of the room during this talk. Other questions? Oh, Antoine, did you have a question? We can't hear you if you do.
Well, I actually have a question, but
Great, go ahead.
Thanks for your nice talk, Sarah. But I'm afraid the question is a little bit more on the theory side. So, of course, it's a very old idea from RVB that if you're going to fractionalize the electron and pair the spinon with a D-wave dispersion according to forming a U1 spin liquid, that's kind of a caricature of the pseudogap behavior. So is there more, or is there a new idea in this paper you just mentioned? I'm afraid this is just a theory question. Sorry about that.
So actually, the paper that I mentioned from Jules' group, I think that's the one that explains these things a little bit better.
No, he's asking about Subir's paper.
I'm asking about Subir's paper and Henry.
Yeah,
one. Sorry.
Yeah. Okay, I think, yeah, so I'm not the best person to answer that question, but I think that I found that even though that I don't understand it very well, but there's this nice comparison between two different fields, right? Quantum spin liquids on frustrated magnets and superconductivity on pseudogaps. But yeah, I'm pretty sure they explained it really well in the paper.
I'll read it. Thank you. That's an incentive.
Thank you.
Okay. Other questions? So can you just say a little more about the energy scales? And this is particularly because the detailed spin liquid fit to the specific heat worked at fields less than, what was it, 0.15 Tesla?
Yes, exactly.
Right?
Yeah.
So this is an anisotropic XXZ model.
That's correct.
And so in the low energy sector, you said this, but I forgot. How big is JZ and JX?
Okay, so that's a very good question. So, so the J values, if you're just looking at the Curie-wise fit, it's basically about 5 Kelvin. So it's 0.05 MeV, right? But when you look at the J1, J2 model, so the range for the quantum spin liquid and the range that we used for interpreting our neutron data is something around 0.12 J2 over J1. So the expectation is that you practically need to be at around 100 millikelvin for this range to be effective. So, and when you look at the 100 millikelvin and convert this to mu BH, that would be very low fields.
But wait, I'm sorry. So this is a triangular lattice,
yes,
but with a J1, J2.
Yes.
But the statement is that the spin liquid physics will emerge only on scales smaller than J2. If we just say J1 is the basic scale.
Yes.
So the reason why all this is very small is the relatively small value of J2.
That's right.
In this compound.
That's right. Yes. Yes.
Okay. And that means that the higher energy things that you did recently with Dole or higher plateaus, that's really just probing the J1.
That's correct. Exactly.
Sure you have
exactly.
a sort of
so
basic, that's independent of spin liquid. In some
yes,
sense.
what is driving the spin liquid is our thermodynamic measurements of a specific heat and the dynamics that we see with AC susceptibility.
Right.
But if you put that aside, because neutrons are MEVs, right? Yeah, exactly right. Yes.
Thank you.
But we still think that there's something interesting happening.
Sorry, there are things I know about hyperfine coupling and nuclear spins that may not apply here, but if they do, then I think what you're doing by just subtracting and forgetting is probably not
right
leaving things. So how large is the hyperfine coupling? Especially compared to these scales.
I don't remember it off of my.
Is it similar to homium?
It is not similar
it's
to
not
homium.
similar.
Yeah. No.
Yeah, because the nuclei are statistically in the high temperature phase, so they're random and they're very slow. So one worries that if the hyperfine coupling is at all comparable to the electron spin physics, then those electrons
actually it is significantly lower.
Okay.
The values, yeah. So it's e to the minus 10 something.
I see.
Yeah, it's right.
Because crystal field parameters tend to be kind of like Coulomb.
Yeah. Yeah, but the value, and even for other compounds for ytterbium, it's actually rather very small. Yeah.